This code snippet is a set of instructions for installing various packages related to statistical modeling, time series analysis, technical analysis, and machine learning experiment tracking in an interactive environment like Jupyter Notebook. The commands include upgrading the stats models and ARIMA packages, installing the TAL library for computing technical indicators, and adding MFlow for managing machine learning projects. These packages are commonly used by data scientists and analysts for data science and machine learning projects. This code imports various libraries and modules for time series analysis and machine learning experimentation. These include pandas for data manipulation, matplotlib, pyplot for creating visualizations, statsmodels, sustatools, ketfuller for checking for stationary time series, sclern, metrics for calculating accuracy metrics, numpy for numerical computing, ARIMA for automatically selecting ARIMA model parameters, and MFlow for managing the MOLE file. This allows for the execution of time series analysis and machine learning tasks, with the ability to evaluate model performance and track experiments. This code performs various tasks, including splitting a data frame into training and test sets, setting up a plot with specific dimensions and font size, enabling the grid for better visualization, and adding labels and a legend. It then displays the resulting plot for the user. The code creates a function called split that divides a dataset into training and testing data for machine learning. It takes in two arguments, the dataset and a list of features. The function first extracts the closed column from the dataset and transforms it into a two-dimensional array to be used as the target variable. It then selects a subset of the dataset using the provided features list to create the input features. Next, it imports the train-to-split function from the sclern modulation module to split the features and target arrays into training and testing subsets. The function sets the train size to 80 and ensures that the data is not shuffled before splitting. The function ultimately returns four variables: train, texttest, and chytest, which can be used for training and evaluating a machine learning model. This Python code helps scale and normalize datasets, especially for machine learning applications. It takes two Celler objects, inputCeller and outputCeller, as well as training and testing feature and target datasets trained. PyTrain, texttest. The inputCeller is applied to fit and transform the feature data, while the outputCeller is used to normalize or scale the target data. The function then returns the transformed datasets and the fitted outputCeller, which can be used for inverse transformation. This snippet is commonly used in the preprocessing stage of a machine learning workflow to improve the performance of the model. The given text outlines 5 lists of Python code containing features related to financial data and technical indicators used in stock market analysis. These lists, named phone to F5, have varying levels of complexity and include items such as moving averages, average true range, ovulation distribution index, and price information. Each list serves as input for further analysis or modeling, with different lists potentially being used for different purposes based on the desired level of detail or sophistication. This code uses the ARIMA package to determine the optimal number of differing terms in an ARIMA model for time series analysis. Specifically, it imports the NDIFS function from the ARIMA module, applies it to the closed column of a data frame called trainFi, and uses the augmented Dickey-Fuller additive test with a 5 significance level to determine the recommended order of differencing D. The resulting number is saved in the chatfidifs variable and printed as the suggested number of differences needed to make the time series stationary. This Python code snippet uses the ARIMA model for making predictions on a time series dataset. The code takes in the dataset a list of features and an option to scale the data. It then splits the data into training and testing sets and applies min-max scaling if needed. The code trains the model by using the augmented Dickey-Fuller test to check for stationarity, setting maximum values for P and Q parameters and considering seasonality. It then predicts the target variable for the test dataset and calculates confidence intervals. The code also employs a walk-forward validation approach for more accurate forecasting. Where the model is updated with new data points, it finally returns the predictions, confidence intervals, and model objects for both the initial and walk-forward validation models, along with the actual test values. This code aims to assess the performance of the ARIMA model in forecasting time series data and simulates a more realistic scenario where new data constantly updates the model. This technique is useful for understanding how the model would perform in a production environment. The following Python function, makeplot, creates and shows a visual representation of stock price forecasting over time. It does so by setting the data frame index to datatime type, creating a figure with specified dimensions and resolution, and adding a title, labels for the axes, and a shaded area representing the predicted stock prices with a confidence interval. The function also includes a legend and the option to save the plot as a PNG file. Its purpose is likely to analyze and compare the accuracy of a stock price forecasting model using true market data. The function evaluate in Python calculates 3 error metric terms, MAPE, made to measure the accuracy of predicted values compared to actual values. These metrics can be used to assess the performance of a model and compare different predictive methods. The Python code snippet is a function call named makeplot. It creates and displays a graph or plot. Using the past parameters, these parameters include statistics, which likely contains the test data, a prediction system, possibly from a machine learning model or statistical method, representing confidence intervals for the predictions, say test, the actual target values to compare against the predictions, and a string literal shifty used to label the plot or specify plotting style. Overall, this function is used to generate a visual representation of a supra-vector-based model's predictions, including confidence intervals, compared to the actual observed values from a test dataset. The makeplot function is used to generate a visual representation, likely a plot or chart, by passing 5 arguments to diff representing the test dataset or related data, predictions suite which contains predicted values from a support vector machine model, confidence suite which is the confidence interval for these predictions, test which is the actual values for the test dataset, and TSD which is a string used to label the plot or specify the model being plotted. This function aims to compare the predictions from the support vector model to the actual values, taking into account the confidence intervals to assess the accuracy and precision of the prediction.